Hi friends, so today we are going to start the second part of set theory. So here first topic we will start would be Venn diagram. So far we have been studying set theory. So most of the things that we studied can be represented in the form of diagram, and that's most of the time much more easier to understand. So we will see how a Venn diagram is created. So So suppose we have a universal set U which consists of 1, 2, 3, 4, 5 and 6, and we have other set A which is a subset of the universal set, which is let's say 2, 3, 5. So we have to represent the same thing in Venn diagram. So what we will do, we will draw a rectangle. So this rectangle denotes the universal set U, and all the other subsets of this universal set. Suppose we had another set B also, or C. So all the other subsets of this universal set, uh, we will draw a circle inside that rectangle. So that rectangle, outer rectangle, denotes universal set, and this inner circle represents set A. And so for now we have just represented the what is universal set and what is set A. Now we will also represent the elements of the set. So first we will write down the elements. So A has 2, 3 and 5. So we will write 2, 3 and 5 inside this circle because these elements belong to this set A. Now whatever is left, so 1 we have not written, so we will write 1. So 1, 2 we have already covered, 3 we have already covered, 4 we have not covered, so we will write 4. 5 we have written, 6, so we will write 6. So in this way, the same information can be represented in pictorial form. So now see that here the universal set has 1, 2, 3, 4, 5 and 6 elements inside it, and this rectangular box is universal set. So all 1, 2, 3, 4, 5 and 6 all lie inside this rectangular box. So we have represented this part. Now 2, 3 and 5 are inside A. So here also 2, 3 and 5 are inside A. So this information is also represented. So this was a simple example of how to represent this info in Venn diagram. Let's see some another example. So suppose our universal set is same as earlier, 1, 2, 3, 4, 5 and 6, and in this case we have A is, let's say, 2, 3, 4, 5, and we have another. So A is clearly a subset of universal set, B would also be a subset of universal set, but B is also a subset of A. So what would be subset of? Let's pick 3 and 5. So how would we represent this? So first of all we would draw a rectangle. So this is our universal set, and then we have A, this is A, and B is a subset of A. The same way A is a subset of U, we draw it inside U. B is a subset of A, so we draw inside B, inside A, sorry. So B we would draw inside A. Now we have to write the elements. So B has 3 and 5. A has 3 we have already written, 5 we have already written. So remaining elements of A are 2, 2, 3, 4 we have not written, 4. So now all the elements of A are inside A, 2, 3, 4 and 5, and all the elements of B are inside B. And now we will see universal set 1. 1 we have not written, so we will write 1 here. 1 is not inside A, so we have to write it outside. 2 we have already covered, 3 we have already covered, 4 we have already covered, 5 we have already covered, 6. So we will write 6 here. So for this example, this would be the Venn diagram. So now we will see some operations that we can perform on a set. And first operation we will call union of set. So this would be represented by symbol U, kind of U. So we will call this union, and it would be equivalent of our common language that we use in English, or. So to understand this, so we will write A union B, and we will read it as A union B, or we can say A or B. So we will treat union as or. So if we see a definition, we will write it like we will define it as A union B is equal to X, such that X, or we will write it in symbol so in the last lecture I had said that this symbol means belongs to. So A union B is a set of elements X such that X belongs to A or X belongs to B. So if A has some elements, let's take one example. So suppose A is a set which has 2, 4, 6, 8 in it, and B is another set which is 3, 4, 5 and 6. So A union B would be, we have to find all the elements which are in A or B. So first we write all the elements of first set 2, 4, 6, 8. Now we look at the second set. So 3 is not inside A, so we will write 3 here. 4 we have already written, 5 we have not written, so we will write 5. 6 we have already written, so we have written all the elements that are present in B and all the elements that are present in A. So this would be the union of A and B. So basically we have to list down all the elements that are present in A and B. So how we will represent the union in Venn diagram? So this is A, this is B, and this is our universal set. And now A has 2, 3, 4, 6, sorry, A does not has 3. So 2, 4, 6 and 8. Now B has 3, 4 is here, and 5. 3, 4, 5 and 6. So here 4 and 6 are common to both. So we have all this part. So this complete region we would denote as A union B, this complete area, because it will cover all the elements that are present in A or B and also the common elements. So now let's move to our second operation. So second operation we would see would be intersection of two sets. So here in union we had taken all the elements that were present in either A or B or both, but in intersection we will only find out the elements which are common to both. So intersection, so I had said that union we will treat it as OR, right? So for intersection its symbol is this. For union it was upside down, and this is reverse, and we will call it AND. So the first one was OR, this is AND. So the same way here we were looking at all the elements that are present in A or B or both. Here we will look at only those elements which are present in both A and B. So we can define X such that X belongs to A and X belongs to B. So the key point to note is the word AND here. So here in the definition we had OR, here we have AND. So if we see at the same example, we will take the same example and draw a Venn diagram. So what are the elements common to both? 4 and 6. 4 and 6 common to both, and here are other elements. So this region we will be calling as A intersection B. This region. So this is A intersection B. And here the entire region. This was A union B. So now we will move on to our third property, or we can see some properties of intersection. So A intersection B is same as B intersection A, because both denote the elements that are common to both A and B, and we had earlier seen in our previous lecture that the order in which we write the elements is irrelevant. That is, whether we write 2 4 6 or 4 to 6, both are same. So both are conveying the same information, the elements common to both A and B, and this is called commutative law. So this property of intersection is called commutative law. So next we have A intersection B and combined intersection with C. So this would be same as so here first we are finding elements which are common to A and B, and then we are out of those common elements and the elements in C, we are finding the common elements. So A, B and C, so this denotes basically the elements which are present in all A, B and C, and the same information is present here. So we can quickly draw one Venn diagram also to see this. So the first one is A, second is, let's say, B, and the third is C. So first we are here finding A intersection B, so it would be this region. Then we are finding the intersection of this region and C, so only this part is common between this earlier shaded region and C. This part is common, so this region is common to all A, B and C. The same thing we will do here, B and C, we will find this region, and then we will find common with A, so it would come as this region. So we see that both are same. And we give a special name to this property also, we call it associative law. So this was commutative law, this is associative law. And third we will see A intersection phi is equal to phi. So what is phi? Phi is an empty set, so it has no elements, and A is some another set which has some elements. So what is the common, what is the element that is present in this as well as this? So this has no element, so clearly there is no common element. So intersection with phi always gives phi. And next property is intersection of an element with itself, it will give the same element, because suppose A has elements 1 2 and 3 and we are finding the common element between 1 2 and 3 and 1 2 and 3, so all elements are common because both are same. So intersection with itself will always give the same set. Next we can see so in associative property we had all intersection here. So here we have first is intersection, second is union. So this will be equal to A intersection B union A intersection C. So if we treat this intersection as multiplication and union as addition, then all these formula you can directly, this would be a shortcut kind of thing. So if you multiply A multiplied by B plus C, so what we will get, A multiplied by B plus B, A multiplied by C. So this is and this is or. So we can prove it using the Venn diagram quickly. So this is A, this is B, and this is C. So first we find B union C. So it would be this region, and then intersection with A. So it will give this part. Now look at this, A intersection B, this part, and this part. So you can take some example and prove it by yourself. You can also use Venn diagram to prove it. It's very simple. You can remember this, which can be used later. So let's continue. We had seen two properties, two operations on set. Let's quickly move on to third operation. We will call it difference of two sets, and we will denote it using minus, like A minus B. So A minus B simply means all the elements X such that X belongs to A and X doesn't belong to B. So quickly we will take some example. So A minus B, we would see that X should, all the elements which belong to A, so those elements are 2, 4, 6, 8. So this first part is satisfied. All elements that belong to A we have written, and all the elements that does not belong to B. So out of these, this only satisfies first property. The second is that it should not belong to B. So whatever elements are present in B, we will remove them. So 2 is not present here. 4 is present here. So we will remove. 5, 6 is present in B. So we will remove here. 8 is not present in B. So A minus B would be 2 and 8. And diagrammatically, we can draw A, B. So this part would denote A minus B. So this complete thing was A, and this part was common to both B. This part was present in B also. So from A we remove this common part. So this green part, this will denote A minus B. And we can see why it works. So A has 2 and 8 here, common elements, and 2 and 8 here, and 4 and 6 here. So you can see that 2 and 8 comes in this part. So this was our third operation. So fourth operation we will say is complement of a set, and suppose we have set A, then its complement we will denote it as A prime, or we also write A and then some small c here, or we can also write A bar. So here most of the time we will be using this A prime to denote A complement. So A complement, it simply means complement means kind of opposite. So if we, this is a universal set and this is A, so this is universal set, so this part is A, so all the elements which are not inside A, so this outer part, so these elements are not inside A, so this will be called A complement. So there should be no common element between A and its complement. So we can give some formal definition. So A complement is the set of elements X such that X belongs to U and X doesn't belong to A. So all the elements which are in U excluding the elements of A. So this will give the complement. So we can write A prime equal to U minus A. So we have subtract from U, we have removed all the elements which are present in A. So here in the difference we had seen that A minus B means from A remove all the elements that are present in B. Similarly, from universal set we have removed all the elements which are present in A. Now we will look at some properties which will help us in solving some practical problems. So first property is N. So remember, N of A denotes cardinality of A, that is number of elements present in A. So N of A union B is equal to N of A plus N of B minus N of . So the number of elements present in union of A and B is equal to number of elements present in A plus number of elements present in B minus elements common to both. So why this is true? So here we have A and this is B. So what is A union B? Remember this complete region. A union B is this complete region. This is A union B. And this part is A. So we take all the elements in A and we add all the elements in B. So we see that this part is added twice. So this is present in A as well as B. So this part is included here also and here also, but this should come only once. That's why we subtract the common elements. So you should remember this so that you don't need to see it every time using diagram. So you can remember it. And the second would be just extension of the first one. We can prove it using the first formula itself, but it's better to remember it. So this time we have three sets and we are finding the number of elements in A union, B union, C. So similarly we will have three sets and A union, B union, C represents this region. So we have to count the number of elements in this. So this will be NA plus NB plus NC. So we have added this, we have added this, we have added this. So this part was added, this common part between A and B was added while adding A and B. So we will subtract N A intersection B. Similarly, while adding B and C, we added this region twice. So we subtract N B intersection C, and similarly A intersection C. So we have subtracted this region, and this region. And this region we have, this was common to all the three. B intersection C, A intersection B, and A intersection C. So we have subtracted it 3 times. So we will add this region again. So you can remember this formula also. It would be useful. These two formula would be very useful. So now we will take some practical examples where we will use these formulae, the intersection, union, complement, and these properties. So our question is, suppose in a class of 20 students who play cricket or football. Of these, 12 play cricket and 4 play football, or 4 play football and cricket both. So class has 20 students who either play cricket or football, and out of these 12 play cricket and 4 play both cricket and football. So we have some questions. How many play? So first question is how many play football. Second would be how many play football but not cricket. And third question is how many play cricket but not football. So now let's solve this. So we are given 20 students who play cricket or football. So remember, or means union. So we will denote cricket using C and football using F. So we are given C union F, that is 20. And then next we are given is N of C, number of players who play cricket is 12. And 4 play both cricket and football. So we have N C intersection F. So here it was or, that's why we used union. 4 play cricket and football, so we are using intersection. So now our first question is how many play football. So we have to find NF. So here we have to find NF. Here we have to find football but not cricket. So here we have to find football minus cricket. And here we have to find cricket but not football. So we will draw a diagram. So this is our C, this is our F. So this complete region is 20. These two combined. And this C this part is 12. So clearly we see that this complete region is 20, this part is 12. So this part alone, this part here would be 8, right? So this part denotes only football because we have removed this part. So this part alone is 8, this part is 12, combined this region is 20. So this is F minus C. So we have got this answer, this is 8. And now we have to find the intersection of this. So we can write N. So remember this formula here, A union B is NA plus NB minus A intersection B. So NC union F is equal to NC plus NF minus NC intersection F. So now we will substitute the values. So this we are already given 20. 20 is equal to NC we are already given 12 plus NF we are not given, NF minus we are given this region, this is 4. So this part is 4. So either we look in the diagram or we solve this equation. So this will be 12 minus 4, 8. We will go this side. We will get NF as 12. So from diagram we see that this part is 12, this is 4, so this is 8. So this part is 8 plus 4, 12. So number of players playing football is 12. C minus F. So this is C, this is C. We subtract this part. So we will get this part, and this part is 12. So this is 12. So 12 players play cricket. Sorry, this complete part is 12 and this common part is 4. So this part is 8. So 8 players who play cricket only, 8 players who play football only. So 8, 8, 16 and 4 players who play both. So we get total 20. So you can use either a Venn diagram or you can write these formula. Using these formula you can find the answer. So so with this we will wrap today's lecture. So you need to practice more questions in order to get proficiency in these. So I had taken very basic examples just to clarify the concept. You need to practice more if you want to gain mastery over this. So thanks.